Hello, everyone. My name is Bing. I'm an engineer on the infrastructure team at Slack. Today, I'm going to talk about scaling Slack. Before the talk, I want to do a quick poll. Raise your hand if you have used Slack before. Wow. I saw maybe 95% of you have used Slack. That's fantastic. So for those who haven't used Slack, let me spend 30 seconds introduce what Slack is. Slack is a messaging app. The conversation is organized by channels. You can send and receive messages, get notifications, send DMs to your coworkers, upload files, search for content, and install tools and services that you already use inside Slack. Today, there are over 1,000 apps available inside Slack. Here are some examples of them. Slack is where work happens. Our mission is to make people's working life simpler, more pleasant, and more productive. We launched Slack about 4 years ago. At first, we only have small teams with a few dozen and hundreds of users. Today, we have a gigantic organization with hundreds of thousands of users. The design decision we made back then made sense, showed their limitations. I'll talk about the challenges and problems we run into, how we solved them, and where we're going next. Here are some numbers about Slack's scale. We have over 6 million daily active users, over 9 million weekly active users. The average time people stay connected is over 10 hours, and over 2 hours in active use on a typical working day. Over half of our daily active users are outside of US. This is a simplified version of Slack's architecture. Slack uses a typical LAMP stack, short for Linux, Apache, MySQL, and PHP. In the center, there is a web application. It implements all business logic of Slack. It's backed by sharded MySQL and a job queue system which execute asynchronous jobs. Another important component of the stack is messaging server. It sends real-time events to users. It uses WebSocket protocol, which is a full duplex communication protocol over TCP. It supports multiplexing and is bidirectional. Both the client and the server can push data to the other end. Our client, mobile, desktop, or web, they speak HTTP to web app and WebSocket to messaging server. The problem we had was user experienced slowness connecting to Slack. The problem first showed up in 2015. To understand why that's a challenge, let's take a look at the login flow. Imagine you arrive at your office, you had your first coffee, now you open your laptop and launch Slack. What happens then is your client sends a HTTP post to the server. The server validates your token and sends back a snapshot of your team. Here is a screenshot of the response with top-level objects. There's team, including your team name and the team setting, the list of channels, the list of private channels, your IMs, your group IMs, users, and bots. On the right, it shows the response size with different number of users and channels of the team. You don't need to read too much about the exact number, but the takeaway is the response size can become fairly big, and it grows with the size of the team. I will come back to this in a moment. In this response, there's also a WebSocket URL, which client used to establish the WebSocket connection with the messaging server. Then, real-time events flows in on this WebSocket connection, and your client is ready to use. You can now navigate to channels, send messages, and start a conversation with your coworkers. On that WebSocket connection, there are over 100 types of events. Essentially, anything happening in real time inside Slack is sent to you through those events. Examples of such events include chat messages, typing indicator indicating who is typing in the channel, files upload, files comment, replies to threads, user profile change, user presence change, reactions, pinged stars, app installation, etc., etc. In short, client first download a snapshot of your team. Then it establishes a WebSocket connection, and real-time events flows in on that connection. The client is a eventually consistent snapshot of your team. This design made a lot of sense in early days. The Slack objects, users, channels, messages are stored locally on the client side. This enabled us to support extremely rich user experience, and it allowed us to move fast and experimenting on new features and designs. It worked great for small teams. However, it's not so great for big teams. There are a few problems. The first, team payload is too big. It takes time for the server to assemble them, to transmit them over the internet, and takes time for the client to process them. It contributes to a large client memory footprint. Clients need to process this payload and keep them up to date. It is expensive to reconnect to Slack. Imagine you had a break in the middle of the day. When you come back 15 minutes later, your client needs to sync up all the events that it missed during that time. There can be reconnect storm. If there is a regional networking blip, many users come back online at the same time. The Thunder herd overloaded the servers, which caused cascading failures and takes time to recover. We were aware of this problem, so we did a bunch of incremental improvements. First, we reduced the initial team payload from 3 different aspects. Client stores a timestamp of the objects so that the server only needs to send a delta of those if they are updated since last time. We removed certain objects out, like IAMs that are not currently open. The idea is to establish a WebSocket connection as fast as possible. Then those data can be loaded in parallel while the WebSocket connection is made. Third, we simplified certain objects. For example, we simplified the user image URLs into a hash code. On a 10,000 user team, this change alone saved us a few megabytes of data. We also changed how client bootstrap. Instead of loading the whole world, the client can choose to load one channel first. This is especially useful on mobile. Imagine this use case. You receive a push notification on your phone. You tap it. All you want to do is to be able to reply to this message as fast as possible. So instead of loading the whole world, mobile client loads this one channel first with the current message, a short message history, and users who are mentioned in the history. This was first implemented in mobile, then the web client adopted it. The web client also do a full load in parallel. This reduced user perceived latency by 30%. A few other things we did. We implemented a rate limit. When servers are overloaded, rate limit kicks in so that we only allow a percentage of traffic to go through. We set up POPs around the world, points of presence, to terminate SSL connections closer to the users. We implemented load testing framework. We created big teams and simulate different traffic patterns in a controlled way so that we can find out bottlenecks proactively. We're not only dealing with the scale of teams, we are also dealing with new product features. For example, in late 2015, we launched group IAMs. This caused users to be naturally in more channels and caused the initial payload to be bigger. We also launched emoji reactions. This makes messages to be bigger, and the client and the reactions are synced to client. This makes client more likely to dump his local storage because at some point it's easier and simpler to load everything from scratch instead of applying a delta. Despite of all this, we managed to keep the situation in control with incremental improvements. However, we know that's not enough. We would still run into a problem if an even bigger team signed up with us. We were at risk of outages when many clients dump their cache all at once. It is time for architectural change. The idea is simple: client lazy loading. Download less data upfront and download more on demand. This means a re-architecture of the client code of the client, because client can no longer make the assumption that all data is accessible locally. Sometimes data are fetched remotely from remote servers. When data are fetched remotely, there is networking round-trip time introduced. But still, we want our user experience to be seamless regardless of where the data are fetched. So we decided we want a new service. This service answers client queries on demand. It is backed by cache and sits on the edge of the network, so it provides fast data access. We call this service Flannel. You may ask, why the name Flannel? Any guesses? Well, naming, as we all know, is very difficult in computer science. On the day when the project was kicked off, the lead engineer happened to wear a flannel shirt. That's why. In short, Flannel is a query engine backed by cache. It sits on the edge locations. We examined the objects in the initial payload and moved the biggest object out first, so users, and then comes with channel membership and channels. We tweaked the login process. Now users establish the WebSocket connection to Flannel first. If the user is the first user on his or her team, then Flannel does not have the team data in cache. It goes to web app and loads the data from DB. Then it establishes the WebSocket connection on behalf of the user. If the user is not the first user on the team, then Flannel already have a warm cache. It skips step 2 and goes to an established WebSocket connection directly for the user. Flannel is essentially a man in the middle. It sits on the WebSocket connection between client and the messaging server. On that WebSocket connection, earlier I mentioned, there are over 100 types of events. Flannel passes through all of them to the client. It processes a handful of them to use them to update his cache. Such events are users and channels related. Examples are channel creation, user change their profile, a user joins or leaves a channel. Flannel is deployed to 7 different locations. The red dot is our main region in US East. In the main region, it has the full Slack stack, including Flannel, web app, DB, and messaging server. Flannel is also deployed to 6 other remote regions, and only Flannel is in the remote region. We use a mix of AWS and Google Cloud for our remote regions. Here are some UI examples that is powered by Flannel. Quick Switcher is a quick way to navigate to different channels and users. When you start typing, it gives you the list of channels and user suggestions. When you select one, you can navigate to them directly. If you haven't used it, I highly recommend it. It's Command K on Mac and Control K on Windows. Mention suggestions. In the message box, when you start to type add something, it gives you a list of user suggestions. It also tells you whether the user is in the current channel or not. Channel headbar, it tells you currently you are in general channel and with a bunch of basic information about the channel, member count, and the channel topic. Channel sidebar, it tells you more about the channel. Team directory, it tells you everyone inside this team and allows you to search it. In short, anything related to users, channels, channel membership, and autocomplete is powered by Flannel. Flannel was launched early this year. There was a load testing team with 200,000 users. We had not been able to load this team without Flannel, but now we are able to load it. Flannel serves over 5 million simultaneous connections at the peak and serves over 1 million queries per second. Here is a side-by-side comparison of the team directory loading with and without Flannel. On the left-hand side, it's already loaded. On the right-hand side, it's still spinning. Takes more seconds. Okay. That's not all of it. Evolution of Flannel. The design of Flannel, client lazy loading, requires client to be able to load data asynchronously on demand. However, before Flannel, the web client was implemented in a way with the assumption that data is always available locally. So right before it's about to render user Bob, it needs Bob in its local storage. It's impossible for us to change every word in client code to be able to support lazy loading all at once. So what Flannel did was to implement just-in-time annotation. Let me explain it in an example. Suppose you send a message. You mention Bob in your message, and Bob is not in the Slack client's cache, so that the client has no way to render the message at all. Flannel sits on the WebSocket connection. It sees this chat message. It uses some heuristic to know, okay, the client does not have it. So it generates a synthetic user change event about Bob. Client still uses its old code. It sees this user change event. It upserts its local storage with Bob. Moments later, when the chat message is received, client is able to render the message without problem. In short, just-in-time annotation accommodates our needs without changing 1,000 places in client code. Today, our client evolved. It is able to load data asynchronously everywhere. So we no longer need just-in-time annotation, but it used to be instrumental for us to roll out Flannel, while the web client make incremental changes to support it. Let's take a closer look. Why does Flannel sit on the WebSocket connection? It needs to receive real-time events to update its cache. However, there's a downside. Imagine this use case. Today, you are at QCon. You only check Slack in and out of talks occasionally. You want your coworkers to know that's the case so that they can adjust their assumption about your responsiveness in replying messages. So you change your Slack status to be in a conference. This status change is broadcast to all your coworkers. If you are on a 1,000 user team, Messenger server sends out 1,000 of such events. Flannel, as a man in the middle, it receives 1,000 copies of the same event. This is very inefficient. What we did is we implemented publish, subscribe, pops up. Flannel pops up to a list of users and channels it is interested in with Messenger server, and only get updates for those. This means a rewrite of the Messenger server for it to support pops up. I won't go into details about how we did it, but we implemented. It provides us a few benefits. It saves Flannel CPU with simpler code. We also changed from JSON event to Thrift event. The schema data is much easier to manage. It provides flexibility for cache management. Previously, Flannel loads the team data when the first user connects and unload data when the last user disconnects. It has to do it this way because that's the only way for it to keep the cache up to date. When the last user disconnects, the WebSocket connection is torn down, and Flannel's cache would go stale pretty quickly. Today, with PubSub, we isolate what events Flannel receives from who are connected to Flannel. So Flannel can keep the cache data around longer. Next time, when the first user on the team connects, Flannel already have a warm cache. This helps with the user connect time. Pre-warm cache is currently under development. Let's take another closer look. With PubSub, does Flannel still need to be on the WebSocket path? The answer is no. We can move Flannel out of the path. In fact, there is no need to couple a search query engine with a real-time events path. Once Flannel is moved out of the WebSocket path, it provides better isolation in our architecture. And this is the next thing we're going to work on. So far, I have been talking about the evolution of Flannel because of performance requirements. There's also product requirements. A big one is enterprise grade. Grade is select solution for big enterprise. Inside grade, you can create unlimited number of federate teams by company departments, office locations, or anything you define. Each grade team provides you the same experience that many of you are familiar with. Across teams, you can create shared channels. Across a few teams or the entire grade. At the grade level, it provides management, privacy, and security control. When Flannel was first implemented, we don't have grade in our mind. One important design of Flannel is team affinity. This means all users from the same team goes to the same Flannel host if they're from the same geographic location. This is to guarantee cache efficiency. With shared channels, it means many different teams share the same objects. This makes Flannel to cache duplicated objects inside the cache repeatedly. It's clear we need to do better. We introduced grade-aware cache, which means on a single Flannel host, we store those shared objects in one separate key space, which are referenced by multiple teams. With this change, we saved a lot of Flannel memory. On average, per host, we saved 22 gigabyte of memory and 1.1 terabyte across the fleet. For our biggest customer, it also improves their DB shard CPU usage. The CPU idle increased from 25% to 90%. That is because it's more likely for shared objects to be in cache. So Flannel needs to go to DB to fetch data fewer times. For the exact same reason, this also improves user connect latency. P99 latency dropped from 40 seconds to 4 seconds. In the future, we plan to implement scatter and gather. When requests come in, one Flannel host fetch data from different key spaces, which may be located on different Flannel hosts, and combine them together. Our thinking is this will further improve our cache efficiency. So far, I've been talking about the evolution of Flannel. Let's switch gears and look at client PubSub. This is an interesting feature for performance reasons. If you still remember the example I brought up earlier, you are at QCon, you change your Slack status to be in the conference, and this is broadcast to all your coworkers. In fact, this is unnecessary. Most likely, you are going to talk to a few dozen coworkers most of the time, so only them needs to know your status change. Instead of broadcast everything to everyone, client side pops up is for client to subscribe to a list of users and channels they're interested in, and only get updates for those. In fact, reduce the number of events clients have to process largely improves clients' performance. The first thing we moved to client pops up is presence update. This is a feature when the user goes online or offline, we render a green or gray dot by the side of your avatar. Presence events used to be 60% of all the events in terms of volume due to its volatile nature. On a 1,000 user team, suppose each user flip their presence once. It generates 1 million events. It grows with n squared in big O notation. So what we did is client keeps a list of users in the counter view and only subscribes to their presence. When the user changes their view, it changes the subscription list. This reduced the presence events by a factor of 5 across the fleet, and we're moving more events into this model. Lastly, let's take a quick tour of messaging server. What is messaging server? You can think of it as a big router. It routes events to users. When an event happens on a team, a message is created, a reaction is made, a file is uploaded. Messenger server found this event to the list of users who are supposed to receive them. Messenger server maintains metadata so that it knows where to route the traffic. It knows which channels are on the team and who are connected to which channels. Initially, it was implemented sharded by team, meaning one server is responsible for your team. All the events related to that team goes to that server. This is a single point of failure. When the server goes down, it means you cannot connect to Slack. We have shared channels. Shared channels means there are many shared states among different teams, and we need to copy messages around. Imagine a shared channel which is shared among a few thousand teams, which we do have in production. This makes states management impossible. It's clear we need a plan B. We changed from team sharding to topic sharding. What is topic in this context? Topic is a group of affiliated objects that you define. So a topic can be a user, a specific group of users, a channel, shared or non-shared, a DM, a group DM, a team, or a grid. Events are sent to topics. Topic sharding is a natural fit for shared channels. The events from the shared channel is sent to the topic that representing that channel and sent out to all channel members, regardless of which team the user is on. It reduced user-perceived failures. Now, when a server goes down, it means the list of topics are not available. Very likely, you can still connect to Slack, but you may not be able to access all your channels. With the messenger server re-architecture, we also improved our failure recovery. Previously, when a server goes down, it requires human interaction. An operator needs to come in, run a script, migrate the states to a healthy server. Today, all these are automatic. It reduced failure recovery time from minutes to seconds. Messenger server support pops up. I mentioned earlier, both Flannel and clients subscribe to the list of topics they're interested in and only get updates for those. This improves Flannel and client performance. Messenger Server implemented fan out at the edge. Previously, Messenger Server only sits in the main DC. Today, we move part of the functionality to the edge. This reduced the networking bandwidth between our main region and the remote regions. This is a 2-year journey. We had a problem. We did a bunch of incremental changes. We keep the situation in control, then we did a big architectural change. This architectural effort is across different teams, backend, front-end, mobile, PMs, and product engineers. Our first design of this architecture is not the most optimal. We knew that, but we decided to do it this way because that's the faster and easy way to push out the change. Then we take time to evolve on this architecture. I think this is the biggest reason why we succeeded in such a big effort. And we have a long way ahead. Currently, we are working on pre-warm Flannel's cache, move Flannel out of the WebSocket path, and everything pops up. On the infra team, besides Flannel and the Messenger Server, we are also responsible for job queue and the storage layer. If you are interested, get in touch. Thank you. Now I will take questions.
So one question about your messaging server. Why did you decide to implement PubSub yourself in the server rather than use a middleware or something else to implement it, for example, say RabbitMQ or Redis or any other PubSub systems out there?
We discussed that within our team. The thing is, we already have a system ready there that already implement most of the logic. So when we do the architecture, we feel like we don't need to spend the effort to bring in something completely new. We can just tailor our existing system and be able to support all those new features.
So if the client is doing a lot of lazy loading as opposed to those big payloads coming across the wire, how are you protecting yourself against, death by reconnect? So if your service goes down and you have these clients across the world trying to reconnect to your service, how are you protecting yourself against sort of a thundering herd problem?
Honestly, it depends on how much reconnect we get today. We can only support it up to a certain point. For example, 2 weeks ago, we actually have an incident where this whole service was down because of a thunder herd problem. But actually, that problem is we lost half of our WebSocket connections, and all of them are collecting Slack all at once. We actually didn't handle it well enough today. What happened back 2 weeks ago was AWS ELB was down because ELB cannot scale fast enough. And then we have to set up a new ELB cluster and scale it over time. That's how we recovered our traffic.
Okay, let's thank Bing.